Hi you there. If you are looking for clear and concise explanation of fluorimetry and phosphorimetry, then you have clicked on the right video. In this video, you can expect the basics of fluorimetry and phosphorimetry. We will discuss how the fluorescence and phosphorescence is created, and we will also discuss the theory behind it, like the singlet state and the triplet state. So let's start the video. But before jumping into the video, if you are watching this video on my channel for the first time, please consider subscribing, because the part 2 and 3 of the same series will contain the points like factors affecting fluorescence and phosphorescence, and also instrumentation and applications of fluorimetry and phosphorimetry. So if you don't want to miss any of these videos, consider subscribing the channel and also turn on the notification bell so that you will be updated once I upload the videos. Now let's begin. First, you understand how this fluorescence or phosphorescence is created. You know, there are many substances which can absorb the UV and visible light. So suppose this is the substance, okay, and it absorbs the UV and visible light, okay, UV visible light. Now what happens? These substances lose the excess energy in the form of heat after some time because of the collisions between neighboring atoms or molecules. Okay, so these atoms or molecules, they collide with each other, and in this collision the heat is liberated, and then the absorbed light is lost in the form of heat. This is called as collisional deactivation. But what happens? There are certain substances which are special and they absorb the UV visible light, but they don't lose all the energy in the form of heat. Then what do? They lose a form of energy, a part of energy as heat, but the remaining energy is lost in the form of electromagnetic radiations. Now these electromagnetic radiations will be having higher wavelength than what was absorbed. Okay, so this is process of emitting radiation, and this process of emitting electromagnetic radiation is referred as luminescence. Now in the luminescence, as you can see, light is produced, but it is produced at low temperature. Okay, so luminescence is referred as cold light or light without heat. Okay, light without heat. Why? Because luminescence is produced at a lower temperature. It is not producing any kind of heat with it. So it is referred as cold light. So this is the process of luminescence. Now let's understand what is fluorescence and what is phosphorescence. Okay, so now when you have understood what luminescence is, how the radiation is produced when the substance absorbs UV light, now consider two situations. In first scenario, once the light falls on that particular substance, instantaneously it starts to emit radiation. Okay, and this process is instantaneous. As soon as you start irradiating the substance with UV light, simultaneously it will start to emit the radiation. Okay, this process, and as soon as you cut this source, this emission of radiation will also be stopped. So this is an instantaneous process. It happens immediately. You start irradiating a substance, it will start to emit the light. You stop the irradiation, the emission of radiation will stop. This process is referred as fluorescence. This is referred as fluorescence. Now imagine another situation. You start irradiating your substance. And then just after a fraction of second, you will see the emission of radiation. Okay, it will start to emit radiations. Now the clutch is here. You stop the irradiation In fluorescence, once you stop the irradiation, the emission will also stop. But here you cut the irradiation of substance, still the emission of radiation will go on for a certain amount of time. Okay, so this can be considered as a delayed fluorescence, right? Because the fluorescence, in fluorescence, once you were cutting off the light, the emission of radiation was stopping. But here, when you are cutting the light, still the emission of radiation going on, still it is going on. So it can be considered as delayed fluorescence, and delayed fluorescence is considered or is referred as phosphorescence. It is referred as phosphorescence. Okay, for explaining the theory behind fluorescence and phosphorescence, we need to understand what is singlet state, what is doublet state, what is triplet state, etc. Now these are nothing but the terms which simply define how many number of unpaired electrons are present there in absence of a magnetic field. Okay, and the number of unpaired electrons can clearly give you the idea about the degeneracy. I'll explain you this thing. Suppose this is the orbital where two electrons are there, but they are paired. In this scenario, how many unpaired electrons are there? 0. So n becomes 0. Now this n, number of unpaired electrons, this is number of unpaired electrons in the absence of magnetic field. Okay, so this number of unpaired electrons can clearly give you an indication of degeneracy, means the number of equal energy states. So if there are 0 number of unpaired electrons, the degeneracy or equal energy states will be n plus 1. So for 0 unpaired electrons, you will have 0 plus 1 is 1 equal energy state or 1 spin state. Okay, so this is referred as singlet state. This is referred as singlet state. When 0 unpaired electrons are there, there will be only 1 spin state, and it is referred as singlet state. Now imagine there is 1 unpaired electron. In that case, your degeneracy becomes n plus 1, that is 1 plus 1, 2. That particular state will be referred as doublet state. If there are 2 unpaired electrons, n becomes 2, degeneracy becomes 2 plus 1, 3, and that state can be referred as triplet state. Okay, so this is how singlet, doublet, triplet, quartet, quintet, this is how you will go on with the states. Now when I say a molecule is in singlet state, you immediately have to understand that there are no unpaired electrons. If I say the molecule or the particular electrons are in triplet state, then it is understood that there are 2 unpaired electrons. So this first must be clear. Now if this is clear, let's move on to the next discussion. Now imagine this is the ground state. Okay, this is the ground singlet state. Now just understand, this is the ground singlet state. Now singlet means there is no unpaired electrons. So there are 2 electrons which are paired. So n is equal to 0. It refers to singlet state. There will be only 1 spin state. Now in this state, suppose these are the pi electrons. These are in the ground state. You know there will be 1 pi anti-bonding orbital which is at the higher energy level. So if one of the electrons from ground state goes to higher energy level, that will go to excited singlet state. So I will write it like this. This is your pi anti-bonding and this will be excited singlet state. Okay, so now at this moment both the electrons are in the ground singlet state and you can observe the spin is opposite, so the net spin is 0 in this case. Now what happens, once it absorbs the radiation, it may happen that one of the electron will absorb that radiation and move to excited singlet state. Now there are 2 possibilities. Now just observe carefully, there are 2 possibilities. Either it can go like this, retaining the original spin. If it goes like this, retaining the original spin, you can see this electron there has upward spin, this is downward spin, so the net spin will be 0. Okay, so this electron is now excited singlet state and there are no unpaired electrons as such because the spin is 0. Spin is 0 means the degeneracy will be 1, and so they are one in the ground singlet, one in the excited singlet. Okay, if this happens while going up, while going in the higher energy level, the spin of this electron changes to this. Now you can see in the ground singlet the electron is having upward spin, in the excited singlet the electron is having upward spin, means there are 2 unpaired electrons now, and so this state will be called as excited triplet state. Excited triplet state. So this is your ground singlet, this is your this is ground singlet, this is excited singlet, and this will be excited triplet. So in ground singlet you will have paired electrons, no unpaired electron. In excited singlet, one of the electron will move on retaining the original spin. So net spin is 0, so it is singlet because no unpaired electron is there as such. And if while going up the spin changes and if there are 2 electrons with same spin, then there are 2 unpaired electrons and it goes to excited triplet state. Okay, so this is the explanation for ground singlet state, excited singlet state and excited triplet state. Now let's learn what will happen during fluorescence or phosphorescence. Now see, the electrons are here in ground singlet. Okay, now when the molecule is irradiated with UV visible light, the electrons will not directly go to excited triplet. It is not possible easily. Okay, so what will happen first, one of the electron will go on and it will retain the original spin and it will go to excited singlet state. Now it has 3 possibilities. Okay, now I will draw a particular graph so that you will understand. Suppose here we will take the energy levels, and here we will take the wavelengths. So in ground singlet your energy is very low, and suppose this is your excited singlet state. Now once the UV light is irradiated and the molecule absorbs the UV light, the electron from ground singlet will go to excited singlet like this. Okay, so I'll draw it like this. Now what will happen? There are 3 possibilities. Either all the energy which it has absorbed will be lost through molecular collisions between the atoms or molecules. So all the energy will be lost in the form of heat and the electrons will come back to their original levels, to ground singlet. Okay, this is referred as collisional deactivation. Means all the energy is lost in the form of heat. It is collisional deactivation. It can happen. This is the first probability. So first probability is collisional deactivation. All the energy is lost in the form of heat. Okay, no radiation. Collisional deactivation happens if the excited singlet state is very unstable. If it is very unstable, all the energy will be lost in the form of heat and the molecule will come back to the ground singlet state. Okay. Now second thing which can happen with the excited singlet state is part of the energy will lost as heat and part of energy is lost as as electromagnetic radiation of higher wavelength. Okay, so what will happen? So as the radiation is of higher wavelength, when the electron is losing the energy, it will not come back like this. It will not be superimposing, the emission spectra will not be superimposing on the absorption spectra. Why? Because it is at a higher wavelength. So it will look like the mirror image of the absorption spectra. So this is your absorption spectra and this is your emission spectra. It will look as mirror image of your absorption spectra because the radiation which is emitting is of higher wavelength, right? It is of higher wavelength. So this is, if this has happened, this is nothing but your fluorescence. It is nothing but fluorescence. Okay. Suppose if the excited singlet state is comparatively stable, then it can turn into a metastable triplet state. It can turn into metastable triplet state. Now what is happening in the excited singlet? This is your ground state configuration. This is your excited state configuration, excited singlet. What happens when it transfers to metastable triplet state? The spin changes. Once the spin changes, there are now two unpaired electrons and you have gone for excited triplet state. Now from excited triplet state, the molecule will return back to original state by emitting the radiation of even higher wavelength. Okay, so phosphorescence will be on the extreme right side of this graph. This is your absorption spectra and this will be the emission spectra for phosphorescence. This will be your emission spectra for phosphorescence. This will be your emission spectra for fluorescence. So this is what happens when the molecule returns back to its original ground singlet state. I'll just wind up it. I'll just revise it one more time. When the electrons in the ground singlet state, they absorb the energy, one of the electron will go to excited singlet state without changing the spin. Now if it wants to come back to the original energy level, it has three options. In the first option, it will directly lose the excess energy in the form of heat due to the collisions between atoms, and it will be referred as collisional deactivation. The molecule will come back to the ground singlet state. In the second probability, the excited singlet electrons will lose the energy partly in the form of heat and majoritarily in the form of radiation, and then it will come back to the ground singlet state, and here the radiation emitted will be of higher wavelength than the original radiation. So this will be called as fluorescence, and in certain cases the excited singlet electron gets transferred to a metastable excited triplet state, and from that state it will come back to the original state. In this process it will emit the radiations and it will be referred as phosphorescence. Now as you can see, when the triplet state, excited triplet electron has to come back, it has to shift the spin of it. Okay, it is not in the easier position to come back and get paired. So this is called as the coming back of that excited triplet electron is forbidden by spin symmetry. It is forbidden by spin symmetry. Why? Because it has to change the spin to come back. Now because the spin symmetry is not in alignment, as it has to change the spin, the process is slow, and therefore the phosphorescence, the emission of radiation, continues long after the cutting off irradiation. This is the reason why phosphorescence is referred as delayed fluorescence, because the process of coming back to the ground energy state is little bit longer than fluorescence. In fluorescence, the upward or the excited singlet electron can easily come down because it don't need to change the spin, but here it needs to change the spin to come back, right? It has to be like this. So this is forbidden by spin symmetry, and hence the process is slow. Hence phosphorescence can be referred as delayed fluorescence. Now one more thing I'll tell you. The process, this third step to convert from excited singlet to excited triplet, this conversion is called as intersystem crossing. It is called as intersystem crossing. The molecule which is having this spin, or the electron which is having this spin, is getting converted to opposite spin, and so it is going into the degeneracy of 3, because now there are 2 unpaired electrons. This process of shifting from singlet to triplet is referred as intersystem crossing. So this is the process or theory behind fluorescence and phosphorescence. I hope you have understood the basics and theory behind fluorimetry and phosphorimetry. In the next video, we will discuss the factors. There are 10 factors which affect the fluorescence and phosphorescence. So we will discuss them in detail, and in the next part we will discuss the instrumentation and applications of fluorimetry or phosphorimetry. Okay, so stay tuned with B.Pharmawise for upcoming videos, and I'll see you in the next one. Bye bye.